Hello guys, welcome back to my video once again. So this time I thought of discussing the continuity of the solid state chapter, right? So if I'm not wrong, last time we people were discussing something about the crystal lattice. I remember drawing those big diagrams for you where I had told you something about what is unit cell, what is crystal lattice, space lattice, what are lattice points, right? What is interfacial angle and what are the faces of a crystal system, right? So having discussed all those details, now I think it's the time that we should move on further to study the details about the crystal system, okay? So this time today I will be starting with one of the very first topic which can be written as the types of crystal system. The types of crystal system, okay? So that's the main topic that we'll discuss first of all today. Fine. Now guys, listen to me very carefully. When I'm doing something related to what are the different types of crystal systems, I will be defining the crystal system based upon one category of their constituents particle. So based upon what are the constituent particles which are constituting the crystal, we can define the crystal system into four categories. The very first category is ionic system or ionic crystals. This is the very first category. Moving on to our second category, which can be defined as covalent crystals. So these are the second category of the crystals that we'll study. If I move on to the third category of the crystal, that can be written as molecular crystals. And finally, moving on to the fourth property or the fourth type of the crystal system, which are known as metallic crystals. Okay, so guys, in today's video, first of all, I will be discussing the details of all these four crystal systems. So in order to simplify the thing, I will just be giving symbols to the crystal system. This is this happy smiley, okay, and then this we have a sad smiley. That doesn't mean that it is a bad topic, but just to represent, this is something like I don't know what is happening, and the white one is something like oh, this was happening, right? So these are the symbols which will represent our crystal systems. So beginning with the very first crystal system, which is ionic crystals. So what do we have in ionic crystal system? In the case of ionic crystal system, I will say that the lattice points. You remember I told you in the last video that every time I will be using these definitions, the lattice point or the lattice sites are nothing but these will be made up of ions. Now the ions, you know, can be of two types, right? We can have both the cations as well as the anions being present in the system. So there will be both the positive and the negative charged particles present in the crystal system. So guys, listen to me very carefully. When you are talking about ionic crystals, don't you think like that there is a particular neutral condition. And this neutral condition is to be maintained in an ionic crystal. So this is point number one. And the second is positioning and size of ions. What do we mean by saying when I'm talking about the positioning and the size of ions? Let us discuss these two things in details once again. Listen carefully. If I am drawing an ionic system, let us say for example, let me start with a very small crystal. Okay, so that is the crystal system that I have taken. Fine. Let me say the white spheres that I am drawing here, they represent the cations. So the white spheres are for cation. Okay, and let us say the blue spheres are for anions. Fine. Now listen carefully. If I am saying this white sphere is there, this white sphere is there, this is there, this is there. Then I have one white sphere here, one here, one here, and one here. Do you think the entire crystal system will be stable? No, guys. Positive, 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 positive. If the complete crystal system is there with the positive charges, don't you think there will be lots of repulsion and the crystal system will break out? Right? So all the positive cannot be present there. That means now we must be having certain negative ions which should be present in between. Something like this. So between two positive, if I say there is one negative which is present. That means you need to keep into your mind about the neutrality condition. That means the equal number of positive. Let's say if the cations are 100, then you need to be sure that the anions are also 100. Okay. However, let's say if there are 100 K plus, we need to be sure that there will be 100 Cl minus. Okay. However, if instead of Cl minus I am taking SO4 2 minus, so then we need 50 SO4 2 minus for 100 K plus. Am I right? So I need to make sure that the condition of neutrality is satisfied. Point number 1. Clear? Coming on to point number 2, so we have to be very peculiar about deciding the position of ions, like where the ions will be placed in the system. A cation is generally separated by the cation when anion will come and fit into it. So we will have cation, anion, cation, anion, cation, anion rearrangement. Okay. So guys, this was about ionic crystal. One more thing about ionic crystals which you can remember, that in the case of ionic crystals, the cation, anion, cation, anion, cation, anion interactions are there. And these interactions are also known as electrostatic force of attraction. And you would have learned in physics by this point of time that the electrostatic forces of attraction are very, very strong force of attraction, right? So if you want to break the crystal, let's say if I am dividing it from here, 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 anywhere if I am breaking the crystal, I need to provide lots of energy from outside, right? And this is the reason why the melting point of ionic crystals is really a very high value. Okay? The examples of ionic crystal, if I am not wrong, you can easily predict NaCl, KCl, etc. Okay? So guys, this was the very first crystal system as you can see here. Now we are done with the ionic systems. Fine? Having done this, let me directly move on to the second crystal system. And the second crystal system that I have for you, let me just prepare the board for you guys so that we can move on to the second crystal system. So the second crystal system, as per you can see in the list, is covalent crystals. Let's see the details of covalent crystals. So covalent crystal is generally represented, like I have represented it with a sad smiley. So let's start with a sad smiley now. So covalent crystals. Now see guys, what is covalent crystal? Covalent is what? You know, right? A covalent bond is generally formed by the sharing of electrons. So if the electrons are shared between the two atoms, there will be the formation of a covalent bond. And because of the formation of covalent bond, not one covalent bond, there will be so many covalent bonds that can be formed. There can be an extensive two-dimensional or an extensive giant three-dimensional structure. So the extensive giant three-dimensional structure, because of the covalent bonds being formed, which are formed because of sharing of electrons, are considered to form a covalent crystal. Okay, let me give you an example. One of the most common example of covalent crystal is graphite. And I think in class 10th you would have studied the structure of graphite, how the graphite looks like. See, graphite must be having carbon atoms which are attached to other carbon atoms. One another carbon atom, forming hexagonal layers. So let me simply draw the hexagonal layers here as well. Something like this. And then something like this. Okay, so these layers will be repeated again and again, and then you can say there may be interactions taking place. Right, so there will be interactions, and this is the structure of graphite. And if I am not wrong, you would have studied the layer 1 can slip on to layer 2. So when the two layers can slip on one another, so there will be kind of that friction is not there, right? That is why they are slipping. So this can be used as a lubricant. Right? Similarly, you can also think about the structure of diamond. So graphite is one example of a covalent network solid. Moreover guys, these covalent crystals are also known as network solids. And another example is of graphite. In case of graphite, one carbon atom is attached to three other carbon atoms. Oh, four other carbon atoms, right? So another carbon, this carbon atom can further be attached to four other. Moving on to any other one, this can be further attached to 1, 2, 1, 3 and 1, 4 is already there. Okay. This one, if I talk about, it is already attached to 1, 2, let's say this. So like this it will continue, and the giant structure so formed will be the structure of diamond. Fine. So having done with the, okay, let me just put a sad smiley again, because now we are done with the covalent crystals. Cool enough? Having done with the covalent crystals, let us now move on to the third category of crystal system. And the third category of the crystal system, as per you can see on the board, is written as molecular crystals. So this we are done. Now we need to move on to molecular crystals. And guys, let us understand the details of molecular crystal. Can you think of any example of molecular crystal? Okay. So see, listen carefully. When I am talking about molecular crystal, one of the very basic example of molecular crystal is ice. That means I am talking about water in the solid state. So what exactly is molecular crystal? A molecular crystal is basically defined as the crystal where the lattice sites will be occupied by molecules. So if the lattice site will be occupied by molecules, they will be known as molecular crystal. Like for example, if you would have considered solid carbon dioxide, solid iodine, solid water, all these can be taken as an example of molecular crystals. Okay? So guys, listen carefully. Like when I was talking about covalent crystals, I said that there are covalent bonds which are holding the atoms together in the crystal, right? When I was talking about ionic crystals, I said that there will be ionic bonds or electrostatic forces of attraction which will be holding the cation and the anion together. But now when I am simply talking about molecular crystals, so now I need to figure out what will be the forces of attraction which will hold the molecules together at the lattice site. Okay? So if I talk in the case of water, there can be dipole attraction. So there are chances of dipole attraction taking place in the case of water as a solid in the crystal system. Now see, for example, this we have done in chemical bonding as well, right? So many water molecules are present. Let us consider this as the crystal system. Water molecules are there. Now what is a water molecule? This is one particular molecule which will be considered as the lattice site in the complete molecule. Okay? Considering this, one particular lattice site. Consider another cloud. This is one particular lattice site. So there are so many lattice sites, right? But the lattice sites are occupied by the what? Molecules, right? Now see, this I know is delta plus, this I know is delta minus. This I know is delta minus, this I know is delta plus. This is delta minus, delta plus, right? So if I know all these things, don't you think I can draw this? I can draw this. I can draw this. So what are these? These are dipole forces of attraction which are holding the molecules together in a molecular crystal. Okay? Also guys, if I tell you an example, another example if I take, let's say I am talking about iodine. If I am talking about solid iodine, so what should I write? See carefully. That is a crystal system. So now so many iodine molecules are present. One molecule of iodine. At another point I can see another molecule of iodine, right? Third point I can see third molecule of iodine. Fourth place I can see fourth molecule of iodine. Fine enough? Now see, there is no dipole, right? It is also neutral. It is also neutral because the bond is there which is formed between the same atoms. So there is no delta plus delta minus as such because of difference in electronegativity, right? But I know, right, these electron clouds are continuously moving. So because of the continuous movement of the electron cloud, this is possible that one of the iodine gets delta plus, other gets delta minus. One can get delta plus, other can get delta minus. Quite possible, right? Now, because of the interaction, you can see this can interact here, this can interact there, this can interact here, this can interact here, 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 right? So all the delta plus delta minus will interact with each other. So now the bonds which are operating in the case of neutral molecules where there is no dipole attraction will be dispersion. So there will be dispersion forces of attraction. Okay? So now we are finally done with our third category of crystal structure, which are molecular crystals, right? Okay. So now let us move on. So molecular crystals are also pretty much okay. Finally, moving on to the last category, which is known as metallic crystals. So let us try to understand the details about metallic crystals as well. So guys, if I ask about the details of metallic crystal and the examples of metallic crystal, you can say that so metallic crystals basically can be written where the constituent particles or where the sides of crystal lattice or the lattice points will be occupied by metal atoms. Okay, so now how metal atoms are coordinated with one another? You can say, for example, there is a pool of iron. So there are so many iron atoms. Let me represent one iron atom with one pink, second iron atom, third, fourth, fifth. So guys, these are all the iron atoms that I am drawing. Okay, now you know, right, iron belongs to D block element and it must be having certain loosely held electrons. Loosely held electrons. So when the loosely held electrons are present in the system, then the electron which was loosely held with one iron metal can come here to the other one. This can be coming here, it can go there. So electron of this can come here. So these are the electrons of all the iron atoms, the valence electrons. And now the valence electron will keep on moving in between all the iron atoms. See, they can roam around any of the atom. They will not leave any particular atom aside. They'll roam around everywhere. So when they'll roam around everywhere, so just consider an ant and it's roaming around everywhere. So there must be forces, right? Now one particular electron, if you look at one particular electron, it is being attracted towards this also, this also, this also, this also. And these forces of attraction are known as metallic bonds. Okay? And the examples of metallic crystals are zinc, copper, iron, etc. Okay? So now what was the smiley? The smiley was this. This is also done, right? So guys, now we are finally done with all the 4 different sets of crystal system on the basis of their constituent particles. Okay, I just want you to note down everything so that I can clean the board for you to continue further with the next portion. So please note it down so that we can continue. So guys, I think you people are now done with the types of crystal system, right? So having done this much, I think we should now be proceeding further. And this time when we are gonna proceed further, I'll tell you something more about what is a crystal lattice. What is a crystal lattice and how this crystal lattice is correlated to symmetry elements. Symmetry elements. So that's the complete topic for another 10-15 minutes. Let's see what is crystal lattice and symmetry element. I told you, right, a crystal lattice is nothing but the 3-dimensional arrangement of either the atoms or the molecules or the ions, right, in a regular fashion. So the three-dimensional, let's say the three-dimensional representation or arrangement of atoms, molecules or ions in the regular fashion is known as crystal lattice. Am I right? Now moving on to what is symmetry element. What is symmetry element, guys? Let's say, for example, I am drawing a small little shirt. Okay? There is a shirt that I have drawn which I got from market, and there it's a plain shirt. There is no nothing written on it. It's exactly a plain shirt. Monocolored, nothing. Okay? Now guys, you must have seen when your mom will ask you to fold the shirt, she will generally be starting from the center, right? And when she starts from the center, you can say that this part of the shirt will look exactly similar to this part of the shirt. Am I right? Like if you see this part, it will be exactly same as this part, right? Now this thing is known as symmetry. This thing is known as symmetry. Symmetry means now you should learn one thing, that nature is in love. Nature loves symmetry. And nature has created every one of us symmetrical, right? Everything you will look into the nature is something which will follow the laws of symmetry, because nature loves symmetry. And whenever there is even a slight deviation from symmetry, so we say that it is unsymmetrical, right? So see, you must have seen this common, like you must have heard of this common phrase also, no? You are always advised to be neutral. You are never advised to be very sad or very like in a very sad mood or in a very happy mood, because nature has maintained this balance of symmetry. Whenever you are sad, God will give you something for happiness. Whenever you are very happy, something sad will be there, right? So that is what is symmetry, that is what is balance. You go from here, it is same, you go from here, it is same. So this kind of thing is available in chemistry as well, and this kind of thing is more or less like in almost every crystal it is available as symmetry element. Okay? So there are three kinds of symmetry elements that I will be teaching you today. So there are three symmetry elements which we will be doing today. The very first symmetry element is known as plane of symmetry. This is known as plane of symmetry. Let us understand what do we mean by plane of symmetry. Consider the case of this shirt only. If I am considering, let's say there is a plane. I have taken the plane about the center of the shirt. Let me draw the plane. Okay, let us leave it. Let's draw the plane here. Or better, I'll give you another example. Let's say it's my birthday cake. My birthday is coming, so I have my birthday cake. Let us prepare an awesome birthday cake for me. So I don't have other colored markers. So let me just say some very good design on my cake. Okay, and on the top I have one cherry at the center and some things are there. So around this I have some fruits here. Then I have let's say one candle is here. So one of the candle is here and one of the candle is here. Okay, and let's say there are one is something here, one something here, one something here and something here. Okay, some fruit nuts are there. So that's a cake. and you can see the cake is 100% symmetrical, right? If I ask you to go and take a knife will be very thin, right? Just a sleek. I am asking you to take a big knife, something like this. Let's say my hand is a knife. And if I am cutting the cake in such a way that I started cutting the cake exactly from the center. Okay, so that is a knife. I am going and cutting the cake exactly from the center. Then don't you think this half and this half is exactly looking same? Right? So these two halves are exactly same. So any such plane, you can see here, look at the plane that I am highlighting. So any such plane which can divide the cake into two equal halves can be called as the plane of symmetry. Okay, so this is known as the plane of symmetry because now it is dividing the complete cake into two equal halves, right? Let us see the same thing how it is applied to the crystal system. Consider one crystal system. Okay, so guys, see, this is a crystal system where the ions are present, or let's say the constituent particles are the yellow ones that I have drawn. So there are 8 constituent particles that I have drawn. Okay, now I am asking you to consider any plane. Let us consider this particular plane. So if you cut the crystal along this particular plane, you can see, ma'am, this half is exactly same as this half, right? So this kind of plane is known as plane of symmetry. Moreover, you can consider a plane something like this, the blue plane. You can understand, right? Even this blue plane is the one which can be called, which can divide the crystal into the top and the bottom half, right? And this is known as plane of symmetry, which is the first symmetry element present in the crystal systems. Okay, so moving on to the second symmetry element. So first symmetry element is done. Let us move on to second symmetry element. Like element is nothing, the type of symmetry things people have started calling as symmetry elements. Let's talk about the second symmetry element, which is axis of symmetry. Now see guys, what do we mean by axis of symmetry? Axis of symmetry is any particular axis about which the molecule is symmetrical. Like for example, I can consider one very simple example of a molecule BF3. Okay, I am just considering a molecule BF3 where I know this is F, F, F and center is boron. Fine. Now let us consider this particular axis. Fine. So if you consider this particular axis and you rotate the molecule at an angle of 180 degree. Listen carefully. Suppose I have something this and this. Let's say if this gets static. Okay, this is one molecule and we have another molecule like this. This is BF3. Now I am considering this particular axis. If I am considering this particular axis and I am rotating it by 180 degree, something like this. But the magnet is not here, so I am just putting it back. For your understanding, I told you that you are rotating it by 180 degree, right? So when you rotate it by 180 degree, don't you think this yellow thing will come here? So it will go like this and it will come like this, okay? But for pasting purpose, I am showing it like this. Similarly, the blue one was here, now it will go like this, right? That means if now I take out all these things, let me say I am taking out the chalks. Now you will simply feel, right, this molecule and the one that I have drawn earlier, they are exactly same. And this all happened because I was working at 180 degree with this axis, right? So I have chosen one particular axis about which if I rotate the molecule, we will be getting exactly the same molecule again. Fine. So any axis which is present in the system about which if you rotate, if you bring about the rotation about that particular axis, and if you are finally getting the similar structure, listen to my words carefully. I am not saying same structure. I am saying similar molecule. Molecule will be same. Same molecule is okay, but similar structure. So if the structure of molecule is coming out to be similar, so we can simply say that the axis of symmetry is present in the system. Fine. Having done with the axis of symmetry, now I should be moving on to the third symmetry element, and this third symmetry element is known as the center of symmetry. This is center of symmetry. So listen carefully, what is center of symmetry? Center of symmetry is basically any center which is present in the system about which if you go in all the equal and opposite directions, if you encounter the same groups or atoms, that is known as center of symmetry. Let us say one blue atom is here, one blue atom is here, one white atom is here, one white atom is here, and one pink atom is here, and one pink atom is here. Okay, this may be a three-dimensional structure, but right now I am just taking it two-dimensional. I am considering a molecule at the yellow position. Consider the molecule at the yellow position. So if you consider the molecule at yellow position, don't you think if you go here at the top, what will you encounter? You will encounter a white atom. If you come exactly following the same path at the back, what will you get? You will get again the white atom. So going equal and opposite in these directions, you are getting the same atoms, right? Okay. Consider this one. You go here at the left, you will get a blue atom. You come here at the bottom, again you are getting a blue atom, right? So you are getting the same things. Similarly, you go to the right, you get red atom. You come to the left, you get red atom. That means when you are moving equal and opposite, and if you encounter exactly the same atoms or groups, so when you are going and if you are getting exactly the same atom or group, then we can say that the center of symmetry is present in the molecule. Okay. So quickly note it down so that I can discuss something more in details. Quickly note it down, guys. Finally, guys, we are done with the details about the symmetry elements, right? So now we discussed basically three symmetry elements. The very first of the symmetry element that we have discussed was the plane of symmetry. So the first symmetry element we discussed was plane of symmetry. Second symmetry element which I discussed with you was axis of symmetry. And the third symmetry element that I discussed with you people was center of symmetry, right? So I took into account all the three elements of symmetry. Okay, that is okay. Now guys, see, the crystal structure, the crystal lattice that I was talking about, that is the reason why I have written this word crystal lattice here. The crystal lattice can also be of various different shapes, right? They may be like a cube, they may be like a cuboid. Let us first draw. If I simply draw, you can imagine it to be a cube, right? It is a crystal lattice. Now draw something like this. So it's something like a cuboid, right? So there may be so many different crystal lattice, but now for our class 12th purpose, we will not be considering all these new crystal lattices. We will just be working with a cubical system. We will be moving on with the cubic crystal, okay? And if you talk about a cubic crystal system, and if you take into account all the number of symmetry elements of the plane, of the axis, of the center, then you will end up getting 23 symmetry elements. So overall you can say there will be 23 symmetry elements in all, which will be found in a cubic crystal system. Okay. So now the details of, ma'am, how can we find out all the 23 crystal symmetry elements? You don't need to go into the details of all those things. So having done with this particular thing, I think we can wind up here, because after this, in the next lecture, I will be telling you how on the basis of the symmetry elements, like these symmetry elements we did, right? How on the basis of these symmetry elements, now the crystal lattices can be studied. So in order to make the study little more easier, we will be using the help of symmetry elements, and with that, we will be classifying the crystal lattices. Okay, but guys, again, as per I say in almost every video of mine, this lecture is of very much importance for the next lecture. So it is a prerequisite. So you won't be able to understand anything in the next lecture of mine until and unless you watch the recordings of this particular lecture. So it is mandatory to watch the recordings, revise, understand, and then come happily in my next lecture. So till that time, take care. Bye-bye.